Okay, so this will be our second video over thermochemistry. In this section, we're going to talk about enthalpy and calorimetry, and then we'll do a little on Hess's law and calculation of heats of reaction. So just here at the beginning, enthalpy concerns, or delta H concerns with the heat energy or the heat energy change in a system. The change in heat is going to equal Q as long as the pressure is the same. If the pressure stays constant, then you can just calculate what your Q value is, and it's the same as your delta H. For most of our calculations, that's the one we're going to be concerned with. So, but if it does change, if there is a change in the amount of work, your pressure times your volume, you actually calculate your internal energy plus your work like we did before, and you can calculate what your enthalpy value is. The ones we'll be more concerned with is just calculating what our Q values are going to be from MCAT and from summing the individual enthalpies for each reaction in Hess's law. Okay, so enthalpy or change in the system, you can be calculated like we've done before with bonds broken minus bonds formed. That would be the only time where you have reactants minus products. But in this one, we're going to do our enthalpy values for our products, delta H for your products, minus that value for your reactants. And if your sum value for the reaction is negative, it's going to be an exothermic reaction. Of course, if it's positive, it'll be an endothermic reaction. And here's an example. So for the reaction where you have sodium and water producing sodium hydroxide and hydrogen gas, you guys should know from everything I've taught you that it is an exothermic reaction. They do give you the delta H value here, though. Find my pen. The delta H value is given as negative 368 kilojoules. Now you could write this in the equation on the product side as plus 368 kilojoules. So you can treat it as a product here. And so if you're given that it has 3.5 grams of sodium reacting with excess water, you could simply do a little stoichiometric, listen to me. You could just do a little dimensional analysis problem here and change your grams to moles and then do a mole-to-mole ratio treating that 368 kilojoules as a product. And so for every 2 moles of sodium on the reactant side, so for every 2 moles of sodium, you have 368 joules of energy that is given off. And so you calculate and you solve, and you should get, you should get 28 kilojoules. Now you're going to know that that is energy that is released, so your value needs to be negative. Now in the Mouse equation where I wrote this, I haven't put in negative 368 in my calculation, but that might be a good idea if you don't know necessarily that the energy is going to be released. Okay. Calorimetry, you can't really see that up there, can you? Calorimetry is the science of measuring heat flow in a reaction. What we generally use is a calorimeter. The one that we'll use in class when we do this experiment will be a coffee cup or 2 coffee cups put together, a coffee cup calorimeter. But there are other calorimeters you can use. There's a picture in here of these. But when you use a calorimeter, you're basically performing the reaction and then measuring the amount of energy that is actually absorbed by that system to demonstrate how much is released or absorbed by the actual reaction. The instrument that you're using, of course, is the calorimeter, and the formula that you'll use is going to be your MCAT formula. So your heat capacity is actually the amount of heat that absorbed divided by that increase in temperature. Now, specific heat capacity is the same, but you're just using it in terms of grams. So your specific heat capacity, which is usually labeled C, is your grams per, your joules over grams degrees Celsius. So per gram, how much energy changes for that amount of temperature change. Anyway, here's the calorimeter that we'll use. We don't really have a cover for you guys, although, I'm looking at this and thinking we probably should, but for our short reactions, there's not that much heat loss to the surroundings since water-specific heat is relatively high. But anyway, you can measure the amount of temperature change in terms of the water. This works really well for heats of reaction or heats of solution, and I think we'll do this for sodium hydroxide and magnesium oxide this year. But anyway, this is your setup over here on the right. We did do this in pre-AP. Here's 2 charts. These aren't in your new textbook. This is from the old textbook, so you can refer back to the PowerPoint if you want. The ones that are actually in your textbook now are a little bit shorter, but I will give you guys the specific heat capacities and the heats of fusion and vaporization that you need to solve the problems. So the MC delta T, we actually did this in the last unit where we calculated, phase change for water from, say, I don't know, negative 15 degrees C is ice, to maybe steam at 110 degrees Celsius, and you had a 5-step equation. This would just be the one where you actually had a change in temperature to calculate your Q value. If it is undergoing a phase change, of course, you'll just use whatever your mass or number of moles is times that molar heat of fusion, or what your heat of fusion is in terms of joules per gram. The specific heat capacity for water, of course, is 4.18 joules per gram degree C, or 1 calorie per gram degree C. In terms of constant pressure, you can use this to solve for your delta H value. And it's just going to be M times C times delta T, and that will give you your Q value, which will be your delta H for that reaction. So the energy released as heat is going to be the same as your heat capacity times whatever your mass of your solution is times your increase in temperature. It'll be actually your specific heat capacity, so your MC delta T, and your value is going to be, for your Q value, is going to be in joules. Unless, of course, you use a specific heat capacity that is actually in calories. But the ones that I'll give you will be in joules. So to do an example, see if we can move that out of the way. An example, coffee cup calorimeter contains 150 grams of water at 24.6 degrees Celsius. A 110 gram block of molybdenum is heated to 100 degrees C and then placed in the water on the calorimeter. The contents of the calorimeter come to a temperature of 28 degrees C, so that's your final temperature. What is the heat capacity per gram of the molybdenum? Now, there's two different ways to do this, really. You can do one where you actually calculate the Q for the molybdenum, calculate the Q for the water, the amount of energy absorbed, and then use that Q value for your molybdenum. And that's what I'm going to show you here. But you could set them equal to one another. So you could do MC delta T. You could do it this way. You could say MC delta T for, say, your water. So this will be all your water part, equal to your mass times your specific heat times your change in temperature for your molybdenum. You could do it that way, and it's real easy. You just solve for the C, the specific heat of the molybdenum. But another way to do it is doing it actually separately. And so if you take your Q for your water, plug in your mass of your water, excuse me, and your specific heat of water and your change in temperature, which is going from 24.6 to 28 degrees Celsius, is 3.4 degrees C. You get your energy change is 2132. Now, all of that energy came from heating up the molybdenum, or cooling off the molybdenum, excuse me, cooling off the molybdenum from 100 degrees C to 28 degrees C. So you just do the same thing, take that Q value and plug it in for Q equals MC delta T for your molybdenum, and you can solve for your specific heat. Some of you are going to want to do it as MCAT equals MCAT, and that's totally fine, or you can do it as two separate problems. Just make sure you use the entire value when you plug it back in. So if it's really 2132 point something, use the entire number when you plug it back in to get something more accurate. And so you end up getting 0.27 joules per gram degree Celsius. Here's just some other calorimeters. A bomb calorimeter, kind of the same thing, except it's in a closed system. You can measure these in terms or describe these in terms of extensive or intensive properties. This isn't something we spend a lot of time on, but just to demonstrate that, well, let's go back and look at the definition. Sorry. An extensive property depends on the amount of the substance that you have. An intensive property does not depend on the amount of the substance that you have. So we have some examples here just looking at this. If the number of calories of energy you derive from eating a banana, well, that's got to be extensive because you don't know how much necessarily of a banana that you have. If you're talking about a certain grams of a banana, then that would be intensive. So extensive is just a general property. So if I look at the next one, what's the next one? The number of calories of energy made available to your body when you consume 10 grams of sugar. Well, that's going to be intensive. That's not necessarily based on the amount you have. You know the amount that you have. Here we have the amount of iron present in your blood. That's going to be extensive. If it were the amount of iron present in 2 liters of blood, well, that would be different. Oh, well, here you go. The mass of iron present in 5 milliliters of blood. Okay, well, that's going to be intensive. The electrical resistance of a piece of 22 gauge copper wire. Well, be careful, you don't know how long this piece of wire is or how much mass it is. And so that's actually going to be extensive. If in fact you were told how long the wire was, you knew exactly how much you had, well then that would be an intensive property. And so that's kind of silly, but if it's dependent on how much you have, then it's extensive. If you know how much you have, then that's going to be intensive. Okay, so here, calorimetry can be done in a closed, rigid container. This is called constant volume calorimetry. This could be called a bomb calorimeter. Flash bulb in a calorimeter in a camera is a good example of this. No work can be done since the volume's not going to change. And the heat evolved. You could just calculate the change in temperature times your heat capacity and solve it. Pretty straightforward. What we're going to be using, though, are coffee cup calorimeters. So the problems that we're actually going to see are going to be like the first one, the first example. So Hess's law, hopefully you remember from pre-AP, is basically the delta H, or the enthalpy for an entire reaction, can be the sum of individual reactions. So if the reaction occurs in several steps, you can add the delta H for each one of those steps, and it will give you the delta H for the reaction. So delta H is not dependent on the reaction pathway necessarily. It could be forward or reverse, but the sum of the individual reactions will give you that delta H value. So if it's in reverse, you just flip the sign of that particular reaction, and you can use that enthalpy value. You'll just have to have the opposite sign. If the coefficients in the reaction are multiplied by an integer, the value of the delta H is also multiplied by the same integer, unless, of course, like on the previous problem, you already knew that 2 moles of sodium produced that much heat. In that case, it would be the same for the entire reaction. Okay, so here we have an example. Well, not necessarily an example, but in this particular one, it occurs, you can either demonstrate it occurring in 2 steps, like I have over here. This is 2 steps for this reaction, or in a single step. Notice, though, that you're getting the same value for both of them. Okay, so just because you're showing it in 1 step, you're showing it in 2 steps. Hess's law shows that if you did it in 2 different steps, the sum of those 2 steps will give you the same value as if it were in a single step. That's really all this is showing, but it could have been more than 2 steps. We'll do some of those examples in the homework. Okay. Given the following reactions and their respective enthalpy changes, calculate delta H for this reaction. So here they've given you the enthalpy values for 3 different reactions. And if you sum these reactions together, they give you each of those individual reactants and products. So 2 moles of carbon plus 1 mole of hydrogen is going to give you, what is that, ethine or acetylene. And so you look at this and figure out what you have to do. Kind of a puzzle. So if I'm looking at this, the ethine is a product. And so the only reaction that I'm given here with ethine in it is this first reaction. So I'm going to have to flip that reaction in reverse, flip it. So what I'm going to have to do is multiply this delta H value here, this enthalpy value, by -1, or make it 1299.6. The carbon plus oxygen yields CO2. That's in the right, that's set up correctly. And the H2 plus 1/2 O2 yields H2O. That's the same as well. So go ahead and set it up with each individual reaction. And let's see, set up with each individual reaction. It is possible that you may have to multiply one of them by 2 or by 1/2 so you can get a balanced equation as your product. And in this case, we actually had to multiply the carbon and oxygen addition reaction by 2. So when we multiply those by 2, we'll end up being able to cancel our 5/2 O2 here, our 1/2 O2 here, and our 4/2 or 2 O2 here. And so when I sum this reaction, the carbon dioxides, of course, over here also are going to cancel, aren't they? My carbon dioxides also cancel, and my waters are going to cancel. And so what I'm left with is 2 moles of carbon, 1 mole of hydrogen, producing 1 mole of acetylene or ethine. And so the final product here will end up being, where's my final product here, is 227.7 kilojoules. So once you get them added up, once you get the individual enthalpies set up, just add them together, and your final will be your enthalpy for the formation of ethine, or your delta H for the reaction. Hopefully you remember doing this in pre-AP. We're not going to do a whole lot of reactions in the notes, but there are some in the homework. So here's another example. Heat of combustion from carbon to CO2 is negative 393.5 kilojoules per mole, whereas for combustion of carbon monoxide to CO2 is negative 283. So they're giving you the same thing, but in word form. calculate the combustion of carbon to carbon monoxide. So write down what the two reactions were that they gave you. So here they are here. So these are the two, excuse me, that are given in the equation. So we're trying to go from carbon to carbon monoxide. So looking at this part right here. So what we're doing is we're combining carbon and oxygen to produce carbon dioxide. We're going to need 2 moles. And so that's the reaction. That's our overall reaction. So just by looking at this, I have to have carbon monoxide as a product. So because it's as a reactant here in the formation of CO2, I'm going to have to reverse that reaction. So if I go and I reverse that reaction, oops, doing it again, reverse that reaction, I'm going to end up being able to cancel my carbon dioxides. And I'm going to cancel my 1/2 O2 and left with 1/2 O2 here as well. If I multiply through by 2, I'd get the same balanced equation I have over there, or I could have written this reaction as a mole of carbon plus 1/2 mole of oxygen yields 1 mole of carbon monoxide. Now, if I had done this and it asked for the combustion of carbon, if it asked for 1 mole, I would need to make sure that I did it in terms of 1 mole like I've done here. But if they had asked for the entire reaction balanced, you would have had twice that enthalpy value. Okay. Okay, so continuing, sorry, you probably didn't even know Albert came in here. Okay, standard enthalpies of formation, so that's using Hess's law to solve. One other way I showed you guys to calculate was through bonds broken minus bonds formed. You can also do it in terms of products minus reactants. So if you know the standard enthalpy of formations of the compounds in their standard states, you can go and calculate the heat of reaction from using products minus reactants. So here you can do it as sum all of the products together, sum all of the reactants together, take a difference of the two, and that will give you your delta H for the reaction. Now, if there are elements in their standard states, and hopefully you remember this, that if it's in their standard state, then their values are 0. If it's not in their standard state, then you need to look them up on the chart or be given them in the equation. Now, on the test and on the exam, they're going to be given to you. You don't have to memorize any of them. On the AP test as well, those delta H values for the heats of formation of different compounds will be given to you in equation form or just given to you numerically. Okay, so here's an example. Consider this reaction. ClF3 plus ammonia yields nitrogen, hydrofluoric acid, and chlorine. They tell you that the delta H naught for the reaction is 1196 kilojoules. Calculate delta H for ClF3 as a gas. In this case, you'll have to look these other values up. I'm just going to pretend that they're here, but I'll show you what they are, but you would look them up on the chart. Now, the value for nitrogen, N2, and for chlorine, Cl2, are going to be 0 because that's both of them in their standard states. So my product values are given here. Let's see my pen. The product values here are given here. And the reactant values here are given here. So it's going to be products minus reactants, and the total is going to be 1196. The variable here is the 2 moles of ClF3. Okay, so I don't know if I can actually do that in here. Oh, that's sad. Well, that's okay. We'll see if it makes it go. Interesting. You guys are getting to see me do some interesting things in this video, and I don't want to go back and start it over again. That was kind of strange, but I just got interrupted again and made a mistake, so I just deleted it. But anyway, there's your products minus your reactants. Go solve for the ClF3 just like it was your X value or variable. Simplifying a little bit, and then finally divide by 2 and you're done. Divide by -2, excuse me, and you're done. So just products minus reactants like we've seen in the past. The present sources of energy we're actually going to do when I get back from being gone over Thanksgiving, so don't worry too much about that. If you want to go ahead and read about it, that would be great. But we'll cover it when I get back. Again, I know I said this at the beginning when you guys watch these videos, but go ahead and do the practice test over break and come with your questions on Monday would be best. All right? Miss ya. Bye.